in the video series on work for Math 1452 at Texas Tech University, which is Calculus 2. So in the previous video, we did an example on work lifting an object, a cable. And in this video, we're going to do an example with springs. So we'll just get right into it. So a force of 3 pounds is required to hold a spring that has been compressed 4 inches from its natural length. Find the work done in stretching the spring 6 inches from its natural length. So again, it's pretty clear that this is a work question because we're just asked to find the work done. So again, I like to start word problems by pulling out all the numbers. So the numbers I see are 3 pounds, 4 inches, and 6 inches. And so let's say what they are. So 3 pounds is the force required to compress 4 inches. And so that actually also takes care of this 4 inches. So I'm just going to cross that out because this 3 is only linked to this 4. So I don't need to list the 4 because it's already kind of been talked about here in this description. But let's just kind of think about and visualize this for a minute. So we have this picture here of our spring at rest and then compressing it 4 inches. So think about that. If you have a spring and you compress it, then it requires some force to hold it there. And so, for this particular spring, it's going to require us pushing in with a force of 3 pounds, or else if we let go, it's going to go back to its natural resting point, right? So we can do an experiment and figure out that it's 3 pounds to compress and push that spring in 4 inches. And now we want to know, okay, well, what about the work done if we're stretching the spring 6 inches from its natural length? So again, you can imagine now pulling that spring apart. And if you have to constantly exert a force to keep it there, or else, again, if you let go, it'll go back to its natural resting point. So this is definitely work using springs. Spring work, in my opinion, is the easiest to identify because, well, the question tells you that you're working with a spring. And so then we're going to now be using springs. So we're going to have, oh, there it is. So for our integrand, we're going to need our spring constant and our distance. And then our bounds are going to be the distance stretched or compressed. So that's already been pulled down here for us. So for the spring constant, so for all questions with springs, there's going to be a sentence in the question that gives the force required to stretch or compress the spring a certain length. So that's what was going on here with our 3 pounds and our 4 inches that are always connected. So there's always going to be some force connected with some distance that's going to let us solve for our spring constant. So our spring constant is going to represent a direct variation. So our force is always going to be K times some distance. So depending on your background, if you've taken a physics course, you may have looked into this using Hooke's law that tells us how springs work. Or if you've taken maybe a math course in high school or a college algebra course, may have talked about direct variation where it's K times distance. So these are all different ways to kind of say that it's going to be some K or some constant that relates force and distance, and we need to solve for that constant. It's going to be different for each spring that you encounter. So for this, we're going to go ahead and plug in. Well, we have that force of 3 was required to move 4 inches. So whenever we solve for K, we divide by 4 on those sides. So 3 over 4 equals K. And just so we can keep track of things, you can represent this, this 3 and 4 specifically is relating inches to pounds, right? So this 4 was inches and this 3 was pounds, just to keep track of our units, but that's not going to affect much. So this K is going to be 3 over 4. So that's our spring constant. And then here, our distance for springs will typically be simple. So I'm just going to let our variable be X to represent our spring moving horizontally because that's how I've drawn it here in this picture. You could stretch and compress the spring vertically. However, I've just drawn it horizontally here. And the distance is just going to be X. So contrary to if you saw the video on lifting up a cable, where the cable became easier to lift up the more we lifted it because there was less cable to lift. Springs aren't going to have that kind of inverse relationship where just because we have already compressed the spring doesn't necessarily make it easier to compress or stretch or anything like that. So we're just going to have our variable x as the distance that the spring has been stretched. And for springs, we saw up above our lower bound 0 and our upper bound is 6 because that's the total distance that we're stretching or compressing. And so now we just need to put all of this into an integral. So this integral is simple to set up. So we have 0, 6, and our force was our spring constant times our distance, right? Exactly here. Force was spring constant times distance. So we're going to have 3 over 4. And now our distance is variable, so it's going to just be represented by x dx. And now we integrate this. So I'm going to pull the 3 over 4 out as a scalar multiple. And then I'm going to use my reverse power rule. So I'm going to add 1 to the power and divide by the new power. And then I write my bounds. So first I'm going to go ahead and simplify this to be 3 over 8 x squared, evaluated from 0 to 6. So now I use my first fundamental theorem and I plug in my 6 first, and then my 0. That 0 is going to go away to 0. And so this is just going to be 3 times 36, which is going to be 108 over 8. And I can simplify this to be 54 over 4, which simplifies again to be 27 over 2. And then this is going to be joules. So that's how much work we have whenever we stretch our spring 6 inches. Okay, and that's all there is to it. So like I said, spring questions are easier to identify because, well, they tell you that you're working with the spring, but then most of the work is going to be in identifying the spring constant because the distance here is also a little bit simpler because it doesn't have that inverse relationship like we had for the cables. So that's going to be it for video number 3. We'll have video number 4 talking about our last example. But for now, we hope this helps and good luck.